Now the next subtopic is fundamental theorem of arithmetic. What does the fundamental theorem of arithmetic state? It states that every positive composite number can be expressed as a product of positive integral powers of prime numbers. And this factorization is unique except for the order in which the factors appear. Now what is a composite number? A composite number, if you have studied earlier, a composite number is a number which has factors other than the number and number 1 itself. So any number which has more than two factors, one factor would be 1 and the other is the number itself. So any number which has more than two factors is said to be a composite number. Now it says that for any composite number you can factorize it in prime factors. You can factorize it into prime factors. You can have prime factors having different powers of them, but the number of the factors would be unique. For example, if you have the number you can see here, it's 140. 140 is a composite number, right? It has more than two factors. When you start factorizing it, you see that 2, 5, 7 are the unique prime factors of 140. So their powers can be different. So it's 2 square 5 into 7. There are three ways in which you can factorize this number 140. So there are three different orders in which the factors 2, 5 and 7 are written. So the fundamental theorem of arithmetic states that any composite number can be factorized into prime factors with unique combinations. So the prime factors would be unique, but the order in which you write them could be different. So you can write 140 as 2 into 2 into 5 into 7, or you could write it as 5 into 2 into 7 into 2, or you could write it as 7 into 5 into 2 into 2. So the order has changed, but the uniqueness in the prime factors has not. So any composite number will have fixed unique prime factors, and this is what the fundamental theorem of arithmetic states. How do we use it and where do we use it? We are going to see it now. For example, in this question, there is a factor tree that we have. What is a factor tree? Factor tree is kind of a tree here where you have the parent node, the first node, the first box that you can see at the top. That's called the parent node. So for each parent, there will be two child nodes. Each parent node is going to have two child nodes. And what you do is when you write the first composite number in the parent node, you factorize it into two factors. You get two factors of it. They may not both be prime. One of them has to be prime. So for 140 in the last question that we took, you had 2 as a prime factor. So the prime factor always has to be on the left hand side child node, and the right hand side node could either be a prime number or a composite number. So you write the composite number in the right node. The left node, you have to remember, it always has to have a prime number. So that cannot be factored. Only the composite number node can be factored into two more child nodes. So the right node will always be either composite or prime. If it is a composite number, it becomes a parent node. Again, you can factorize it. You have two child nodes. The left hand side will have a prime node. The right hand side should have a composite node or a prime node. So you go on bifurcating, you go on factorizing the right hand side node until you arrive at a position where both the child nodes, the left hand child node and the right hand child node, they both become prime numbers. That is when you stop, and then you count all the left hand bottom two nodes and all the left hand child nodes. If you go on multiplying them, you are going to arrive at the value of the parent node. That's the composite number that you started with. So based on the factor tree, we are going to do this question. We have to find the missing numbers in this factor tree. So what do we have? In the factor tree, as it says that the left node will be a prime number. It always has to be a prime number. The right node, you keep on filling a composite number. At the last step, it will always be, the factor tree is going to stop at a point where both the nodes become prime. So in this, what you see is, this is just a part of the factor tree in this particular question, because in the last two nodes you can see the two nodes are 2 and 165. 165 obviously is a composite number, but the factor tree doesn't go beyond it. It means this is just a part of the factor tree, it's not the complete factor tree. So you have 2 into 165, since we do not have to find the numbers below 165, we should not be worried about it. Let's see what will be above this. So the parent of 2 and 165 will be the product of these two numbers. So the parent right before 2, right above 2 and 165 will be product of 2 and 165, and that's going to be 330. So you have 330 and then 2. What will be the parent of these two numbers? The parent of these two numbers will be product of 2 and 330, which is 660. So the two boxes that you can see here, at the top level it will be 660 and at the second level it will be 330. Now let's take another factor tree. Now this has, you have to find out the missing numbers A, B, C, D, whatever it is. Now we always start in a factor tree, we should start with the bottom, but here we can see that the number A can be directly arrived at. A is what? 2 into 1260. At the top, A is the parent node. It will be the product of its two child nodes. The two child nodes are 2 and 1260. So the product of 2 and 1260 would be how much? It will be 2550. So it will be 2520. So A's value will be 2520. Now 1260 is split into two factors, B and 630. Now 630 into B should be equal to 1260, as 1260 is the parent of B and 630. So what do we get the value of B as? It will be 630 into B. The equation will be 630 into B is equal to 1260. Therefore B is equal to 1260 divided by 630, that's equal to 2. So the value of B is going to be 2. Now coming to the number C, you have 2 into C is equal to 630 because 630 is the parent. So C's value will be 630 divided by 2, that's going to be 315. Now C is 315. 315 will be equal to 105 into D. So D will be 315 divided by 105, that's equal to 3. So you have D is 3. Now 105 is split into two factors, X and 35. So 35 into X is equal to 105. Therefore X's value will be 105 divided by 35, which is equal to 3. 35 is split into two numbers, Y and 7. So Y into 7, 7Y will be equal to 35. And Y will be 35 by 7, that is equal to 5. So Y's value will be 5. And since the bottom two nodes have prime numbers, we can conclusively say that this factor tree is a complete factor tree.